This is my intermediate algebra course. Today we're going to review transformations and learn the library of relations. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. We'll start by reviewing transformations. We went over transformations in my geometry course. We covered the four basic types. Translation is when you change the position of an object, but you don't change the orientation. So this side is the bottom of the triangle, but it's still the bottom of the triangle. This side is at the left of the triangle, but it's still at the left of the triangle. So you're not rotating or flipping around, you're just changing the position of the object. A rotation doesn't really require an explanation, you're just rotating the object. But be aware, with rotations, you need a center of rotation. If your center is up here, then when you rotate a triangle that's down there, for example, then your triangle is going to go along that path. But if your center of rotation is at the center of the triangle here, then the triangle is just going to rotate around like so. So it depends on the center of rotation. Now it's important to understand that when you learn transformations in the math curriculum, typically rotation is not really covered much because the math involved is pretty complex. You need parametric equations and trigonometry, and so typically rotation is just not something that's covered when we introduce transformations. So we're not really going to go over that. So you don't have to worry about that. The third type of transformation is reflection, and that's when you flip an object over some line. And the reason that this is called reflection is because if you have a mirror, let's say that this line here is a mirror, and you set this triangle in front of the mirror, well, what do you see in the mirror? You see this red triangle. So that's why this is called reflection. And be aware that you need a line of reflection. You always need a line of reflection. If your line of reflection is over here, for example, then that means that your triangle is going to flip over this way. Sorry about that, the ink is a little big there, but so that's why this is called reflection. Now these three types of transformations are called rigid transformations. Rigid meaning that the size and the shape of the object do not change. But the last type of transformation, dilation, that's a non-rigid transformation because the size of the object actually does change. And be aware that with dilation you need a center of dilation. If your center of dilation is here, then the object is thrust outwards like so. If your center of dilation is in the middle of the triangle, for example, then you thrust out like so. If you're making the object bigger, or if you're making it smaller, it would move inwards like so. But we don't have to worry about a center of dilation for the math curriculum. Center of dilation is really not covered in the K-12 math curriculum, or even when you go into upper math. Again, like rotation, it's just not something that's focused on in the curriculum. Sometimes you'll see it, but 99% of the time it's not something you need to worry about. So we're not going to really go over the center of dilation, but we are going to dilate objects today. So we're going to cover those three transformations: translation, reflection, and dilation. You also need to know what a relation is. Now we've already learned relations. For example, these equations here, these are relations. We just didn't call them relations. They're referred to as relations because it gives us a relationship. Each one of these equations gives us a relationship between x and y. And there's three different ways to write a relation. You can write it as an equation in those examples, or you can write a relation with tables in those two examples, or you can write a relation as a graph with these two examples. So all three of these methods express the relation between two values. A relation is a connection between two values, usually called x and y. That's another way to explain it. Now, this is a really important part of the curriculum because we're going to learn something called the library of relations, and you're going to use this library from now until the end of your math education. These are also called parent relations because we're going to create a lot of complex equations that are modifications of these basic relations. Typically, you'll hear the library of relations referred to as the library of functions, which we're going to learn in subsequent classes. But we haven't learned functions yet in my curriculum, so we're just going to call these relations. And you see that we have the three ways to write these relations. We have graph form, equation form, and table form. So we've already learned the linear relationship. This is the most basic linear relationship possible, y equals x. Again, these are parent relations, so we're trying to simplify them as much as possible. We're going to use these as a framework where we can modify these equations. Quadratic, we learned that the graph of a quadratic relation is a parabola. That's the most basic parabola that we can see, y equals x squared. We're also going to learn some new graphs that we've never graphed before. For example, the square root graph. We have never graphed y equals square root x. Well, that's what it looks like right there. And by the way, these arrows mean that the graph continues forever. There's the cubic relationship, y equals x cubed. That's what that looks like. And we're going to learn these other relationships in the next class. So we're going to cover the linear relationship, quadratic, square root, cubic, and the absolute value relationship. We're going to leave the reciprocal, exponential, logarithmic, and greatest integer for probably the next class. Now the greatest integer relationship, a lot of people might look at that and think, well, what in the world is this? Well, I just added this here. We're probably not even going to cover that in this class. You may see that a couple times in the math curriculum, but it's just not something that's really focused on much. So I just threw that in there to have something fill that space, but we're probably not really going to cover that graph much in this curriculum. So the first thing that we're going to cover, again, we have our four transformations. The first thing we're going to cover is translation. And by the way, I want you to get a screenshot of those library of relations or take a picture with your phone. You're going to need to use that shot at the left there as we go through the class today. Please get a picture. You must get a picture now. I don't want to have to keep going back and forth. So get a picture with your phone, get a screenshot. We're going to use that for the rest of the class. But the first thing we're going to cover is translations. Now, if y is changed to y minus k in an equation, then its corresponding graph is moved up k units, assuming that k is positive, of course. If y is changed to y plus k in an equation, then the equation's corresponding graph is moved down k units. And the same is true if you add or subtract to x, but when you add or subtract to x, you move the graph to the right or to the left. Now, a lot of people would say, whoa, wait a second, I think you got that backwards. If you subtract a number from y, that should move the graph down, not up. Well, actually, it's the exact opposite of what you would think. If you subtract from y, it actually moves the graph upwards. And none of that really has any meaning whatsoever unless we can do some practice problems and see how this works. So it says here, write the parent relation and the parent equation of each relation below and use this information to graph the modified equation. This is the modified equation here. So first we need to write the parent relation. And how do we know the parent relation? Well, we see this is a square root expression, so the parent relation is going to be the square root relation. So that's pretty easy. The parent equation, if you look at your library of relations here, you see that the parent equation is y is equal to square root x. So we're going to write that. Again, please, if you have not taken a picture of the library of relations, do that now. We need to have that right in front of us as we're doing this. So the parent equation is y is equal to square root x. Now, notice that we have x minus 2 instead of x, and we have y plus 3 instead of y. So this basic equation here has been modified, and we're going to use the parent equation circled in red to kind of help us understand what the graph is going to look like when we put it on this grid. So let me show you how this works. If you graph this parent equation, it's going to look like so. We have a reference point at 0, 0, and we have a reference point at 1, 1, and we have a reference point at 4, 2. And we can connect the dots, and there's your graph. Now you might be thinking, whoa, where did you get these reference points? Well, I'm looking at my library of relations. We have a reference point in purple at the origin. We have a reference point at 1, 1, and we have a reference point at 4, 2. And you also have the table down there in orange. So those reference points are extremely important. You're going to learn those reference points. You're going to understand how to find those reference points using this graph if you forget the reference points. You're going to learn how to use those reference points as a framework to graph these shapes. And you're going to be required to do this and remember how to do this. This is one of the most important things in the entire curriculum, the library of relations. Typically, students forget these basic relations and their graphs and equations, and it plagues them for their entire math education. That's not going to happen to you. You're going to know these like the back of your hand. So I found those reference points by looking at the graph, or you can look at the table, and we have our basic, you can call it the parent graph. Now, the reason that I graphed this is I want to show you what happens to this graph when you make these modifications to the equation. Notice that we subtracted 2 from x. What that's going to do is it's going to move the entire graph 2 units to the right. 1, 2. Now again, I know what you're thinking. You're thinking that's not correct. You're subtracting 2 from x, you should go 2 units to the left. But it's the exact opposite of what you would think. It's not 2 units to the left, it's 2 units to the right. When you subtract, you go to the right or you go up. And if you add, you go to the left or down. It's the exact opposite of what you would think it would be. Now, a lot of students might say, well, why is that? Give an explanation of why that is. Well, the explanation is not really going to be that helpful to you at this point. We could give an explanation, but it's not exactly something that is obvious. If you want to know the explanation, then give me a comment in the comment section, and we can go over that. But it's not really something that you need to know right now. It's not something that's really going to be that enlightening to you, in my experience. Now, we're adding 3 to y. So not only are we going to go 2 units to the right because we subtracted 2 from x, but because we're adding 3 to y, we're going to go 3 units down. It's not 3 units up. It's 3 units down. It's the exact opposite of what you would think it would be. Now we're going to erase that arrow because we went out of our window. We're going to draw a new arrow there, and we're done. That's it. That's how a translation works. We translated the graph 2 units to the right and 3 units down. And that's all this is. That's all a translation is. When you change x, When you subtract units, you move it to the right. When you add units to y, you move the graph down. Now, there's one really important thing I need to mention, and that is that you don't have to graph the parent graph first, because that's going to be a huge waste of your time. You don't want to have to graph the parent relation and then erase that and then graph the new modified relation. The reason that I'm doing that is I'm just showing you how the graph moves as you modify it. I'm just giving you the basic idea here, but you don't have to do that. What you want to do is graph reference points. We had that reference point at 0, 0. We moved 2 units over and then 3 units down, and then you have your new reference point here. And then, if you notice, the graph goes up 1 and over 1 to get a new reference point, and then up 1 and then over 3 to get your second reference point. That's how you want to do it. You don't want to really graph the parent graph, because that's going to be a lot of work. So let's go over some more problems here so you can get an idea again what's happening. The parent relation, you see this is a square. It's x plus 3 squared, so that's going to be the quadratic relation. Again, look at your library of relations. I'm going to give you one more chance to take a picture here. There's your library of relations. Get a picture with your phone or a screenshot. You need to have that right in front of you. You can look online for this library of relations. It's going to be called the library of functions, though. So watch out for the library of functions if you're going to look for a picture online. So this is the quadratic relation, and the parent equation, if you look on your library of relations, the parent equation is y equals x squared. So now, again, you want to use reference points. You want to use 0, 0. You can see on your library of relations, 0, 0 is a reference point. You see here, we have 0, 0 in purple. We have 1, 1, negative 1, 1. And we have 2, 4. We have a negative 2, 4. You can use all those reference points to graph your parent graph. Now, again, you don't have to graph the parent graph. I'm just doing this just to show you the basic idea. So 0, 0, and we have 1, 1, negative 1, 1. We have 2, 4, and negative 2, 4. You can use symmetry. And then you just connect the dots. Now, that's the parent graph. You don't have to graph the parent graph. I'm just showing you the basic idea. Now, we're adding 3 to x. So that means we move the entire graph 3 units to the left. Again, it's not 3 units to the right. It's 3 units to the left. Then we're adding 3 to y, so we move 3 units down. Not 3 units up, 3 units down. And there you go. That's how it works. Now, again, you don't want to graph the parent relation. I'm just doing that to show you how this works. What you want to do is you want to use a reference point, which is 0, 0. That's the vertex of the parabola. And then again, move 1, 2, 3 to the left, 1, 2, 3 down. And then you can use that basic framework. The shape of the graph is going to be the same. So notice when we were up here, we went over 1 and up 1 to get the next point. So we can go over 1 and up 1 down here to get the next point. And we can go to the left and up to get the next point. Sorry, my program is kind of jumping around there. So to the left and up 1 to get to the next point. And then we can go to the left 2, and then up 1, 2, 3, 4, using that basic framework. Because again, when you were over here, you went over 2 and then up 1, 2, 3, 4. So you do the same thing down here, over 2, up 1, 2, 3, 4. This is what you're going to do to actually graph the equation. Now we can also graph some more points here. So if you look at your basic equation here, if you plug in 3, 1, 2, 3, and you square it, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. But the problem is it goes out of the graph. But when we're down here, you don't go out of the graph. So we can actually graph that point. 1, 2, 3 out, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice how I'm using this equation, this parent equation, to graph the shape. Now we just connect the dots. And there you go. All right, so that's how you're going to graph the equation. You're going to use a reference point. So let's try another one here. We'll speed up a little bit. So what parent relation is this? Well, obviously it's the absolute value relation because we have an absolute value. So that's the absolute value relation. The parent equation, if you look at your library of relations, the parent equation is y equals absolute value of x. And you can look at your graph. You know there's a reference point at 0, 0. And it says we're going to add 6. So we're going to move over 1, 2, 3, 4, 5, 6. And it says subtract 4 from y. So that means we're going to move up. Remember, it's the exact opposite of what you would think. We're going to move up 4. So then we have our special point there. And then if you look at your graph, notice that those lines go through the diagonals of the boxes. So that's all you need to do is just use a reference point and then draw your graph after you translate that one reference point. But if you were to draw this graph, the parent graph first, just to demonstrate, you don't have to do this, but I'm just going to do this so you can see what's going on. This is the parent graph that's on your library of relations. And when you translate, when you add 6 to x, you move the whole thing 6 units up, or 6 units to the left and 4 units up. All right, so that's how that works. But you don't have to do that. I'm just doing that so you can see, again, how these translations work. So again, you want to notice these little features of these graphs, that those lines, they go through the diagonals of those boxes. These are all things that you're going to slowly learn over time, and yes, you will know this stuff like the back of your hand. You need to remember these graphs, remember these basic equations. We're going to do this stuff so much that you're just going to learn this naturally. So you don't have to worry about memorizing these graphs now. So now the parent relation is going to be the cubic relation because we have a cube. So that's the cubic relation, and y equals x cubed is the parent equation. So again, the graph is going to look something like this if you look on your library of relations. But we're going to move the whole thing over 1. So we're going to use that reference point at 0, 0. We're going to move over 1, and then we're adding 5 to y. So we're going to move down 5 units. 1, 2, 3, 4, 5. Again, it's the exact opposite of what you'd think it would be. You would think that because you're adding 5 to y, you'd go up. It's not true. So now, look at your framework. Look at your graph. You know that if you go up 1 and over 1, you get the other point. Again, if you look at your graph on your library of relations, you have a reference point there, and then you go up 1 and over 1, you get another point, and if you go down and to the left, you get another point there. So that tells us the framework. So we're going to use that principle down here. Now, if you look at this equation here, sometimes we have to use the equation as we did in the previous problem. When you go out 2 units, that means you plug in 2 to x, and then if you cube 2, you get 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that goes off the window there. But when we're down here, again, the shape doesn't change. The basic shape doesn't change. So if you go out 2 here and go up 1, 2, 3, 4, 5, 6, 7, 8, you see we can actually mark a point on the graph there that's not out of our window. So you're going to get used to the basic shapes on the graph, how to use the equations, how to use a reference point, so on and so forth. So if you draw this graph, it looks something like that. And be aware that this is not an art class. Your graph doesn't have to be 100% perfect. You just have to have those reference points. And the cubic graph is a little more difficult to graph than the other ones, but so those 4 problems give you an idea of how this works. So I want you to try number 5. Identify the parent relation. You see that it's a square root here, so obviously the parent relation is going to be the square root relation. You need to have that library of relations right in front of you, so try number 5. You can use numbers 1 through 4 to help you, and when you come back, we'll do it together. Alright, we're back. So the parent relation is obviously the square root relation. The parent equation is y is equal to square root x. And we can use a reference point. So 0, 0 is on the parent graph. And we're going to add 1 to x, so that means we're going to move to the left 1. And we add 4 to y, so we're going to move down 1, 2, 3, 4. So that's our new reference point there. And we know, based on the shape of our graph, if we go up 1 and over 1, we get another point on that shape. And if we go 1, 2, 3, 4 units over and 2 units up, that gives us another point on our shape. And so then we can just connect the dots, and that's it. That's the graph. So if you got that graph, good job. Again, all you're doing is just moving that shape around. That's what translation is. You're just taking this shape and moving it 1 unit to the left and 1, 2, 3, 4 units down. That's all we're doing here. It's really not difficult. But the parent graph helps us to understand, what shape we're moving around. So go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. Obviously, we're squaring, so this is going to be a quadratic relation. That's the parent relation. Y equals x squared is the parent equation. And if you look at your graph, it looks something like this. That's the parent graph. So we're going to move, we have the reference point at 0, 0. We're going to move that 1 unit to the right and 1, 2, 3, 4 units up. Again, because you're subtracting 1 from x, which means you go over 1 to the right, and you're subtracting 4 from y, which means you go up 4. So then we can use our framework. You go over 1, up 1, you get your next point. And over 1, up 1, you get your next point. Use that framework, and then just connect the dots. So if you got that basic shape, good job. Go ahead and try number 7. And you can take a screenshot of these problems up here if you want to use those to help you. Go ahead and try number 7. And when you come back, we'll do it together. All right, we're back. We see an absolute value symbol here, expression, so it's obviously the absolute value relation, and the parent equation is y is equal to absolute value of x. So if you look at your basic graph, it looks something like this. I didn't draw that perfectly, but you get the point. It looks like a V. So you can use the reference point at 0, 0, move that reference point 1, 2, 3 units to the right, because we're subtracting 3 from x. Whoops, my computer's going kind of slow here. So 1, 2, 3 units to the right, and then 1 unit down because we're adding 1 to y. So then your lines are just going to go through those diagonals. That's something that you have to memorize about the absolute value relation. Your lines always go through those diagonals. And that's it. So that's what your graph should look like if you got that right. Good job. Okay, go ahead and try number 8. This relation is a little bit more difficult than the other ones, so try number 8, see what you can do, and when you come back, we'll do it together. All right, we're back. We're cubing x minus 2, so this is a cubic relation, and the parent equation is y is equal to x cubed. And if you look at your graph, it's going to look something like that. So we can use 0, 0 as a reference point. And we're going to move that reference point 2 units to the right because we're subtracting 2 from x, and we're going to move 2 units up because we're subtracting 2 from y. Now if we go to the right and up 1, we get our second point. If we go to the left and down 1, we get our third point. And up here, the line's going to approach those boxes, but it's not actually going to get to those boxes. Now down here, if we plug in -2, we should go down 8. Again, that's looking at your framework. If we consider this to be the xy axis, again, it's the same shape. So if we go over 2 units to the left, we should go down 1, 2, 3, 4, 5, 6, 7, 8 units. So our other point is going to be down here. And so that's roughly what your graph should look like. Again, the arrows just mean that you're moving, the graph actually continues up forever, or continues down forever. So if you got that graph, good job. Now, you need to be aware that you can actually flip these equations around. Sometimes you can write the y is over here and the x is over here. That's perfectly fine. Remember, you can flip an equation around. It doesn't change the equation of the graph created by the equation. So the parent relation, we see this is a squaring x plus 4, so the parent relation is a quadratic relation. And the parent equation is y is equal to x squared. If you want to, you can write x squared is equal to y. It doesn't make any difference. So if you graph that, it's going to look something like this. So we see we have a reference point at 0, 0. And again, that graph is not perfect. I'm just graphing that quickly. So we have 0, 0. And we want to move that 1, 2, 3, 4 units to the left and 1 unit up. So now we go over 1 up 1, to left up 1, over 2 up 4, to left 2 up 4. Again, this is the same shape as the parent graph that you have in your library of relations. So we know how to graph that framework. Go over 1 up 1, to left up 1, to the right 2 up 2, to the left 2 up 2. These are the things that you need to get used to as you're graphing these parent graphs. Okay, so I want you to try number 10. This equation is different because it's flipped around. The y's are on the right side of the equation. The x's are on the left side. When you come back, we'll do it together. All right, we're back. So this is obviously the square root relation because we have a square root. And the parent equation is y is equal to root x. If you graph that parent equation or parent graph, you don't have to graph it, but if you graph it, it looks like that. And so we see that we have reference points. I'm going to use the reference point at 0, 0. And I know that if I subtract 3 from x, I'm going to move over 1, 2, 3. And if I add 1 to y, I'm going to move down 1. So that's my new reference point. Looking at your library of relations, you see the framework. You always go up 1 and over 1 from that reference point to get your next point. And you always go 1, 2, 3, 4 units to the right and up 2 to get your next reference point. That's a little bit outside the window there, though, so you have to be careful. And there's your shape. So if you got that shape, good job. Okay, so now we're going to learn the last last parent relation that we're going to learn today, and that's the linear. Notice that there's no complex operations going on here. There's no square roots, there's no cubes, there's no squares, there's no absolute value symbols. There's nothing except just y's and x's and normal numbers. That means that this is the basic linear relation. And the parent equation is the most simple equation that you can possibly see. Basically, that's y is equal to x. Actually, there's probably some simpler equations, but that's when it comes to lines, that's pretty simple. It's the most basic form. So if you look at your library of relations, you know that the line just goes through the diagonals of the boxes. That's what the parent graph looks like of the linear relation. So as usual, what you're going to do is you're going to use a reference point, and you're just going to, because we're translating the graph, you're just going to move this shape around. We're going to move it 2 units to the right and then 6 units down. And that's how this works. But we're going to use that reference point because we don't want to have to draw the parent graph. So we had a reference point at 0, 0. We're going to move 2 units to the right and 1, 2, 3, 4, 5, 6 units down. So now that's our new reference point. And we can just move up through those, the diagonals of those boxes and down in the same direction, and that's it. All right, so I want you, well, let's try number 12 together. The parent relation is obviously, again, the linear relationship, and the parent equation is y is equal to x. 0, 0 is a reference point we use, so we're going to use 0, 0, go 1 unit to the left and 1, 2, 3, 4 units down. Then we're going to draw our line through the diagonals of these boxes, and that's it. My graph went a little bit weird at the end there, but you get the point. All right, so now it's time for you to try. Go ahead and attempt number 13, and when you come back, we'll do it together. All right, we're back. This is obviously the linear relationship. The parent equation is y is equal to x. 0, 0 is a good reference point, so we're going to start there, but we're subtracting 6 from x, so we're going to move 1, 2, 3, 4, 5, 6 units to the right, and we're going to move 1, 2 units up. And again, we want to draw our line through the diagonals of those boxes. That's just how the basic linear relationship works. It has a slope of 1, which means you go up 1 over 1, up 1 over 1, to left, down 1, to left, down 1. So if you got that graph, good job. Go ahead and try number 14. When you come back, we'll do it together. All right, we're back. Obviously, this is the linear relationship, the linear relation, and the parent equation is y is equal to x. We can use that basic, again, this is the parent graph. It looks like that. So we can use 0, 0 as a reference point and then go 1 unit to the right because we're subtracting 1 from x, and then go 3 units down because we're adding 3 to y. Then we just draw our line through the diagonals of the boxes, and there you go. So if you got that graph, good job. Okay, so that was translations. You can see that all you're doing is just taking these parent graphs and just moving them to the right or to the left or down or up. That's it. It's very easy. If you want to move the graph to the right, you subtract some number from x. If you want to move it to the left, you add some number to x. If you want to move the graph up, you subtract something from y. And if you want to move the graph down, you add something to y. But now we're going to learn the second type of transformation. Again, we're not doing rotations today, or we're really not going to focus on that in the curriculum. But the second type of transformation we're going to learn is reflections. With reflections, what you do is you take y in your equation and you change it to negative y. And what that does is it reflects the graph across the x-axis, not the y-axis, the x-axis. If you change x to negative x in your equation, then you reflect the graph across the y-axis, not the x-axis, the y-axis. Again, that all means nothing unless we do some practice problems. So you can take a screenshot of this if you want to. And we're going to do some practice problems. You're going to see how this works. So let's first identify the parent relation. We see a square root here, so obviously that's the square root relation. And the parent equation is y is equal to square root x. That's on your library of relations. We're using the same library of relations to explain all this. So the only difference from our parent equation and our modified equation is that instead of x, we have negative x. So what does that do? Well, let me draw the parent graph. You don't have to draw the parent graph, but this is what the graph would look like, the basic library graph. That's y is equal to square root x. And to show you what's happening here, when we put a negative in front of that x, what it does is it acts as though this orange y-axis is a mirror. And what would we see in that mirror if we looked from this shape here? Well, we'd see the exact same thing, except going in the other direction. So that green graph there is our new graph. We reflect it across the y-axis. Now, the whole idea of a reflection is it can kind of be confusing. So another way to think about it is what you're doing is taking a reference point, for example, 4, 2, and you're asking how many units, well, what is the distance from that point to the y-axis? It's 4 units. Then we go across the y-axis the same distance, and guess what? We get our corresponding point. So every point over here has a corresponding point over here that's the same distance across the y-axis. That's why we say we reflect across the y-axis. So that, I may have over-explained that, but hopefully you get the basic idea. So I'm going to change this graph to red. And so there you go. That's reflecting across the y-axis. Now notice that when you write a negative on the x, it reflects across the y-axis. Again, it's the opposite of what you would think. You would think changing x would reflect across the x-axis. No, it reflects across the y-axis. So let's try another one of these problems. The parent relation is obviously the quadratic relation because we have a square. The parent equation is y is equal to x squared. But now we have something different here. We have a negative y. We're putting a negative in front of the y. Instead of the green y here, we have the blue negative y. We wrote a negative in front of the y. So what does that do? Well, it reflects across the x-axis. So if you draw your basic graph, you don't have to do this. You only have to draw the reflected graph. But if you draw your parent graph, it looks like that. And if you reflect across the x-axis, what you're going to do is you're going to flip it over. So we have the same graph, except it's flipped over the x-axis. So if you consider the x-axis to be like a mirror, if you're standing here, you see this red shape here. In the mirror, you're going to see the green shape down here. That's why it's called reflecting across the x-axis. Now again, if you want to think about it in terms of moving points across the x-axis, you can take a reference point, for example here, And you can just ask yourself, how many units to the x-axis? Well, that's 4 units. And how many units across to get to that same point? It's 4 more units. So that's another way to think about reflecting. And if you use this point here, you have 1 unit to get to the x-axis, and you go across 1 unit to get to the corresponding point there. So we reflected the graph across. Now, again, you don't have to draw the parent graph. You just have to understand the reflection. So how do you deal with this? How do you graph these? How are we supposed to approach all this? Well, once you start memorizing the shapes of the graphs, it's going to be very easy to understand how to reflect or translate or dilate and so on and so forth. Maybe not so much dilation, because with the dilation the shape actually changes. But when it comes to translating and reflecting, once you know the general shape, you can actually picture in your mind how the graph is going to change. Another important thing to understand is that you can use the equation to find points. I can't remember all the different reference points of certain graphs, but I can look at this equation and I can plug in values, and that's going to help me graph also. You need to use all the tools that you've learned to get familiar with this library of relations. So let's do number 17. Obviously the parent relation is the cubic relation because we have negative x cubed, and the parent equation is y is equal to x cubed. And so we know that the basic graph is going to look like this, something like that. That wasn't perfect, but something like that. And we wrote a negative in front of the x. That means you're going to reflect about the y-axis. So it's going to look something like this. So, but I want to make it very clear. You can use this equation to find points also. So if I plug in 0 into that equation, if I plug in 0 to that equation, then we get 0 for y. Negative 0 is 0, 0 cubed is 0. So we still have our 0 reference point there. And if you plug in 1 for x, negative 1 cubed is negative 1. So you go to the right 1 and down 1. That gives us another point. See how I'm using the equation? You can use the equation. If you plug in negative 1 for x, then you get a double negative. Remember, a double negative is a positive, so this blue part becomes positive 1. You cube positive 1. 1 times 1 times 1 is just 1. So when you plug in negative 1, you get positive 1. And the graph just proceeds from there. It approaches that line, but it never really touches that line. So this is an example where the original graph looked like this, and this side was on the left of the y-axis, so when you reflect, it moves over to the right. This side was on the right of the y-axis, so when you reflect, it moves to the left. So I know that that's kind of confusing, but with reflections that occurs, that happens. Okay, so let's go on to number 18. Let's try a couple more of these before you try one on your own. The parent relation is obviously the absolute value relation. And the parent equation is y is equal to absolute value of x. But now instead of y, we have negative y. So your basic equation looks like this, but because you're adding a negative on the y, we're going to reflect across the x-axis. That means we're going to throw each one of these points across the x-axis, and you're going to get your corresponding point. If you go down 3 here, then you go across the x-axis 3 more units. That's just how reflections work. So again, you can use your equation if you want to, but the easiest way to do this is just picture the shape in your mind. You know that it's just going down. We have the same shape, but your V is going down instead of up. The most important thing is to remember the basic shapes. I didn't draw that too well. But remember the basic shapes and remember the basic concepts of reflection and translation. And this stuff is not going to be too difficult. Okay, so in this problem we have the absolute value relation again. But we're changing x to negative x. Now, in this case, if you look at your library of relations, again, this is the basic parent graph. You don't have to graph this, the parent graph, when you're doing this stuff. But in this example, if you're going to reflect this shape about the y-axis, look what happens. This point here, if you go across 1, 2, 3, 4 to get to the y-axis, it's just a coincidence it keeps being 4. Let's use a different point. So 1, 2, 3, 4, 5 to get to the y-axis. You go 1, 2, 3, 4, 5 more units to get to your corresponding point. But wait a second. There was already a point there. So what you're doing is you're taking all these points and throwing them on these points. And you're taking all these points and throwing them on these points. So what does that mean? It means the graph doesn't change. In this case, the graph actually doesn't change at all when you reflect. That's why I put a purple star here, because this problem is a little weird. That sometimes happens. When you reflect a graph, sometimes the shape actually doesn't change at all. So be aware of that. Okay, so now it's time for you to try. You can take a screenshot of these problems here if you want to, or a picture with your phone. And you can take a picture of this information if you want. Go ahead and try number 20. And when you come back, we'll do it together. All right, we're back. So the parent relation is obviously the square root relation, because we have a root. The parent equation is obviously y is equal to square root x. So you see that on your library of relations. But instead of y, we have negative y. So what does that mean? It means we're going to take our basic graph, which looks like this, and we're going to reflect it across the x-axis. So it's just going to get flipped over the x-axis from here down to here. So instead of going, well, first of all, we can use our reference point 0, 0, and instead of going to the right and up, we're going to go to the right and down. And then instead of going to the right 4 units and up 2, we're going to go to the right 4 units and then down 2. Again, this is all things that you're going to get used to after using this library of relations again and again and again. The whole point of this class is for you to get used to these basic shapes. So if you got that right, good job. Go ahead and try number... sorry, my computer's jumping around here. Go ahead and try number 21. When you come back, we'll do it together. All right, we're back. So the parent relation is obviously the cubic relation, because we have x cubed, and y equals x cubed is the parent equation. And we're changing y to negative y. So your basic graph usually looks like this, your cubic graph. But we're going to flip across the x-axis, so it's going to look like this. And I want you to notice that when you reflect the cubic relation about the x-axis, or across the x-axis, you get the same graph as when you reflect across the y-axis. So sometimes that happens. You get the exact same graph. So if you got that answer, good job. Go ahead and try number 22. what you'll notice is when you reflect this relation across the y-axis, you're going to get the exact same graph. So go ahead and try number 22. When you come back, we'll do it together. All right, we're back. So we can plug in 0 for x and get 0 for y. Plug in 1 for x, negative 1 squared is 1. Plug in negative 1, then you get a double negative. Double negative becomes a positive, and positive 1 squared is 1, so you get 1 again. We can just use symmetry. Plug in 2 for x and you get 4. Plug in negative 2 and you also get 4. And then we can connect the dots. So this is the same graph that you have on your library of functions, because this point is reflected to this point on the other side of the y-axis, and this point is reflected to the other side. So you're just replacing points when you reflect, and you end up with the same exact graph. Same thing over here. You take this point and you reflect it to this point, but you already had that point. And you take this point and reflect it to that other point, but you already had that point. So that's why you get the same exact graph. So if you got that graph, good job. The parent relation is the quadratic relation, and the parent equation is y is equal to x squared. So if you got that answer, good job. Go ahead and try number 23, and when you come back, we'll do it together. All right, we're back. All right, now we have a linear relation. Why is it linear? Because there's no square roots, squares, cubes, or absolute value symbols. It must be linear. The parent equation is y is equal to x. Y is equal to x normally looks something like this, the graph. But because you have a negative in front of the x, you're going to reflect across the y-axis. So all these points are going to move over here, and all these points are going to move over here. And we're going to end up with a graph that looks like so. Now, if you can't picture that reflection in your mind, that's okay. You can just use the equation. You can plug in 0 for x, you get 0 for y. Plug in 1 for x, you get negative 1 for y. Plug in 5 for x, you get negative 5 for y. And you can plot those points just using that equation. So that graph doesn't look perfect, but you get the point. Okay, I want you to try number 24. And when you come back, we'll do it together. All right, we're back. The parent relation is obviously the linear relation. The parent equation is y is equal to x, but now we have a negative on the y, so that's going to reflect across the x-axis. So if you take this parent graph and reflect across the x-axis, it flips down like so. But notice that that actually gives us the same exact graph that we did before. That's because negative y is equal to x is the same thing as y is equal to negative x. These equations are actually the same exact statements. If you multiply both sides of 1 by a negative, then you get the same equation, because remember, you can do something to both sides of the equation. It's not going to change the equation. So if you got that answer, good job. Okay, now we're going to move on to the third type of transformation we're going to study in this course, dilations. I want you to be aware that dilations are much different from the transformations we've studied so far, because dilations are non-rigid. What that means is when you dilate a graph, you actually change the shape of the graph slightly. The basic form is going to be the same, but you're going to stretch it or compress it, so it's not going to be the exact same shape. With these transformations, the shape doesn't change at all. But with a dilation, the shape might get compressed again or stretched. So that's the most important thing to understand about dilations. And I want you to be aware that things can get kind of confusing when studying dilations, because a horizontal stretch can be interpreted as a vertical compression, and a vertical stretch can be interpreted as a horizontal compression. So things can get really confusing. And so mathematicians have decided that when you multiply x or y by a number, it's a compression. If you multiply y, it's a vertical compression. If you multiply x, it's a horizontal compression. If you divide x or y by a number, then it's a stretch. You're stretching the graph. If you divide x, it's a horizontal stretch. If you're dividing y, it's a vertical stretch. So whenever you multiply or divide y, it's a vertical dilation. Whenever you multiply or divide x, it's a horizontal dilation. Now, something else that's very important to understand is when you multiply x or y in an equation, the corresponding x or y values on the graph are actually divided by that number. So it's the exact opposite of what you would think. Remember, when we add something to x or y in an equation, we actually move the graph to the left or down, the exact opposite of what you would think. If we subtract something from x or y in an equation, the graph moves to the right or up. So again, it's the exact opposite of what you would think. When you write a negative symbol on a y in an equation, you reflect across the x-axis. When you write a negative on the x in an equation, you reflect the graph across the y-axis. It's the exact opposite of what you would think. Well, the same is true with dilation. If you multiply x or y by a number in an equation, assuming that number is a whole number, then all of the corresponding x or y values on the graph are actually divided. On the other hand, if you divide the x or y value in an equation by a number, then all the corresponding x and y values on the graph are multiplied. So it's the exact opposite of what you would think. So this can be somewhat confusing, but that's okay. With some practice, you're going to see that this is actually pretty easy. So get a screenshot of all that information there. You can reference that or take a picture with your phone. This is going to be easy, as you're going to find. So the parent relation is obviously the absolute value relation, because we have absolute value symbols. The parent equation is y is equal to absolute value of x. And this is a dilation because we're multiplying x. And because we're doing something to x, it's going to be a horizontal dilation. And what type of dilation? Is it a compression or a stretch? Well, we're multiplying, so it's going to be a compression. Whenever you multiply x or y, it's always going to be a compression. Very important to remember that. So now we just have to graph it. And to do that, we're going to use the parent graph. We're going to start out with the parent graph. The parent graph looks like that. And remember, when you multiply x, that means that you're going to take all the x values and divide them by 3. The exact opposite of what you would think. The exact opposite. I know that's frustrating, that we're multiplying x by 3, but we're going to divide all the x values by 3. I know that's confusing. And we can go over why that is if you really want to know. But you just really have to remember the rule. So isn't it true that this x value here is 4? Let's start with an easier one. Let's start here. This x value is 3, right? So I'm going to divide that by 3, and we get 1. So the y value stays the same. The y value was 3. It stays the same when you move it from here to here. But the x value is a third of what it was before. So we're going to do that on the other side too. This is -3, but -3 divided by 3 is -1. So now we have that point. So the graph is being compressed horizontally. It's being pushed inwards. And again, it can be confusing because the horizontal compression can be interpreted as a vertical stretch. So, don't overthink these things. The point 0, 0 is not going to change. Let's see if we can find another easy point. 1, 2, 3, 4, 5, 6. Divide that x value by 3, and we get 2. Same thing over here. We're going to get 2 there. And now we just connect the dots, and we can get our basic shape. So that's how this works, and you can see that it's really not that difficult. The key is don't overthink this stuff. Just remember the rules. Okay, so now let's try this one here. We are, well, first of all, this is the square root parent relation. And the parent equation is y is equal to square root of x. And this is going to be, we're doing something to y. We're multiplying y, so it's going to be a vertical. Whenever you do anything to y, it's always going to be a vertical dilation. What type of dilation? Well, we're multiplying, so it's going to be a compression. We'll do stretches later on, but now it's a compression. So if we plot this parent equation here, and you can look at your library of relations to help you do this, we get this shape here. It looks something like that. But we're multiplying y, so that what that means is we're going to take all the y values and divide them by 2. It's the exact opposite of what you see here. We're multiplying y by 2. But the y values in the graph, they're all going to be divided by 2. So again, I know that's very confusing. So this y value here is 1, but we're going to divide it by 2, so it's going to be 1/2. And this is 0, so 0 divided by 2 is still 0. This y value is 2, so we're going to divide by 2 and get 1. We're dividing all the points by 2. I think that's about it. That's the only points we can really plug in. So now we just connect the dots, and there you go. So you can see this is really not that difficult. It does take some practice, as usual, but this is not too bad. So now we're going back to the x here. Obviously we have the cubic parent relation, and y equals x cubed is the parent equation. And we're multiplying x, so this is going to be a horizontal dilation. Whenever you multiply x, it's always a horizontal dilation. Or whenever you do multiply or divide x, it's horizontal dilation. But what type of dilation is it? Is it a compression or a stretch? Well, we're multiplying. Whenever you multiply, remember, it's considered to be compression. Okay, so if we graph the parent equation here, or just look on your library, we have 1, 1, negative 1, negative 1, and the graph kind of just takes off. So it looks something like that. But now we're taking all the x values and we're dividing them by 4. Okay, x is multiplied by 4 over here. But in the graph, all the x values are going to be divided by 4. Very confusing. Very confusing. So this x value is 1, so we're going to divide it by 4, and we get 1/4. So it'll be about there. This x value is -1, so we're going to divide it by 4. We get negative 1/4. And if we plug in any more values, it looks like it's going to be off the scale. So now we can go ahead and use those points to graph. So it's kind of scrunched in here, very difficult to graph. But what we did is we horizontally compressed the graph. We pushed it inwards. And I forgot to mention up here, this is a vertical compression, so we pushed inwards, pushed down on that graph. So let's try one more of these before you attempt one on your own. This is the quadratic parent relation, and the parent equation is y is equal to x squared. And we're multiplying y, so whenever you multiply or divide y, it's going to be a vertical dilation. What type of dilation? Well, multiplication is compression, remember? Multiplication is always compression. Okay, so now we just have to graph it. Let's graph the parent equation first. You can look at your library of relations. Don't forget your library of relations. You should have a picture with your phone or a screenshot. That's what the parent graph looks like that we get from that equation. But we're multiplying y, so what that means is we're going to take all the y values and divide them, the exact opposite of what you would think. We're going to divide them by 5. Take all the y values and divide by 5. Now again, it's the exact opposite. This is multiplying. We're multiplying y by 5. But on the graph, you're going to be dividing all the y values by 5. Now again, please don't be troubled by that. The explanation is actually pretty simple, but at this level of mathematics, it may not be beneficial to you to go into that. So let's take a y value. This is 4 here. That's the y value of that point. And we're going to divide it by 5. So 4 divided by 5. 4 divided by 5. Well, that's just 4 times 1/5. Remember, you just flip the divisor and write this whole number as over 1. And then when you multiply fractions, you just multiply the numerators. 4 times 1 is 4. 1 times 5 is 5. Now that is all basic mathematics that you should already know. So we get 4/5, which would be about here. And same thing over here. That y value is divided by 5 and we get 4/5. And this y value is 1, so we divide by 5, we get 1/5. That'll be about there. Same on the other side if we use symmetry. Now, I want you to understand something very clearly here. We're stuck at this point. And the reason we're stuck is because we don't have any more points on this graph that we can just divide by 5. We don't have any more y values that are actually in the window. So we're going to go ahead and erase this graph. We can't really use that anymore. We know that our new graph looks something like this, but we don't know where to go at this point. We don't have any other points. We could just throw it up like that, but we want to be a little more precise. So in this case, we can always go to the actual equation itself. Let's plug in 3. If we plug in 3, 3 squared is 9. Then we get 5y is equal to 9, divide both sides by 5, and y is equal to 9/5. Well, that's a fraction. That's kind of a pain to have to graph. Let's see if we can find an easier value. Let's plug in 5. We plug in 5. 5 squared is 25. So we have 5y is equal to 25, divide both sides by 5, and y is equal to 5. So if x is 5, y is 5. So we found a good point there. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Plot that point. And we can use symmetry. So we have a point over there, and then we just connect the dots. Okay, so the previous graph looks something like this. And we multiplied y, so we compressed it vertically. We pushed the green graph down. That's considered a vertical compression, and it turned into the red graph. So again, I know this can be kind of confusing, but with some practice you can get the hang of this. Okay, so now it's time for you to try. You can take some pictures of these problems with your phone if you'd like, so you can have a reference. Go ahead and try number 29. We're multiplying y, so it's going to be a vertical dilation. Whenever you do anything to y, it's always a vertical dilation. And if you multiply, it's going to be a compression. So go ahead and try 29. When you come back, we'll do it together. Okay, we're back. The parent relation is obviously the absolute value relation because we have absolute value symbols, and the parent equation is y is equal to absolute value of x. This is all in your library of relations. It's a vertical dilation because we're doing something to y, and it's a compression because we're multiplying. We're only doing compressions so far. We'll get to stretches later. So let's graph the parent equation. That looks like this. Again, you can see this on your library of relations, or you can just use this equation if you forget your library of relations. If you have this in your head, you can just plug in values to help us graph that. So now we're multiplying y. So that means we're going to divide all the y values by 3. Divide all the y values by 3. It's the exact opposite of what you would think. So this y value here is 3. So I'm going to divide that by 3, and obviously you get 1. This y value is also 3. I'll divide that by 3, and I'll get 1. This value is 1. 1 divided by 3 is 1/3. Same thing over here. This y value is 6. Divide that by 3, I get 2. Same thing over here. Divide by 3, and we get 2. Whoops, that was not the right point. We need to go over a little bit more. There you go. So now connect the dots, and there's our graph. So this was a vertical compression, which means that we pushed down on the orange graph to get to the purple graph. So if you got that one right, good job. Okay, go ahead and try number 30. When you come back, we'll do it together. Okay, we're back. So this is a square root parent relation, because we have a square root, obviously. The parent equation is y is equal to square root x, and it's a horizontal dilation. How do I know that? Because we're multiplying x. Whenever you multiply x, it's a horizontal, or when you divide x, it's a horizontal dilation. We're multiplying, so it's going to be a compression. Okay, so if you look at your parent graph, your library of relations, square root x has these reference points, 1, 1, 0, 0, and 4, 2. So that's what the parent graph looks like. But we're multiplying x in this equation, so it's going to change the graph. Whenever you multiply x, that means you take all the x values and divide them by that number. Divide by 2. So this x value is 4. We're going to divide it by 2, and we get 2. Divide this x value by 2, and we get 1/2. And let's see, what else can we do? I think that's about it. we're going to go off the scale if we plug in any bigger points. We know if we plug in 8 for x, we'll get 16, and then root 16 is 4. So we know that we can't go any higher than this. So our graph is going to look something like that. You could get more precise with a calculator, but we don't really need to. So if your graph looks something like that, excellent. Go ahead and try number 31, and when you come back, we'll do it together. Okay, we're back. The parent relation is obviously the cubic relation. The parent equation is y is equal to x cubed. This is all on your library of relations. It's a vertical dilation because we're doing something to y, and it's a compression because we're multiplying y. If we graph our parent equation, or just look on our library of relations, we see that the parent graph looks something like this. But we're multiplying y, so that means that we're going to divide all the y values by 3. Not multiply the y values by 3, but divide the y values by 3. So this y value here is 1, so we have to divide it by 3, so it becomes 1/3. This y value is -1, so it becomes -1/3. And we have a y value of 8. When we plug in 2, we get 8, because if that 3 were not there, if this 3 were not there, then if we plugged in 2 to x, we would get 8. But we're dividing all the y values by 3. And if you just use these 2 points, that's probably fine. But 8 divided by 3 would be 2 2/3. So we get another y value there. And then plug in -2, and we get -2 2/3. Again, if you didn't get those other points, that's okay. So now, let's plot. You could find other points to be more precise, but that's okay. It doesn't really, I'm not going to make you be more precise. So we compressed vertically. We took the graph that looked like this, and we pushed it down and we pushed it up. That's compressing vertically. So we're pushing down and up on the purple graph, so it turns into the green graph. So if you got that one right, good job. Okay, go ahead and try number 32. When you come back, we'll do it together. Okay, we're back. So this is the quadratic parent relation, and the parent equation is y is equal to x squared. This is a horizontal dilation because we're multiplying x, and it's a compression because it's multiplication. When you multiply x or y, it's always a compression. So if we graph the parent graph, as we've done already in this class, it looks something like that. But because we're multiplying 4, or we're multiplying x by 4, we're going to take all the x values and do the exact opposite. We're going to take all the x values and we're going to divide by 4. So this x value is 2. So we're going to divide by 4 and we get 1/2. This x value is -2, divide by 4 and we get -1/2. And this x value here is -1, divide by 4 and we get -1/4. Same thing on the other side. And I think that's about it. Our graph is going to have some pretty big y values after that. And of course 0, 0, that doesn't change. So we compressed horizontally. We took the graph that looked like this, something like that, and we compressed it horizontally. We pushed in from the right and in from the left, and we turned it into the purple graph. Okay, if you got that one right, good job. So now we're just going to do a linear example. If you look at your library of relations, y equals x is the linear parent equation. So this is a linear parent relation. Y equals x is the equation, and looks like we're doing something to x. So it's going to be a horizontal dilation, and it's multiplication, so it's going to be compression. So let's draw the parent graph. It's going to look like this if you look at your library of relations. But we're going to take all the x values and divide by 3. Again, it's the exact opposite of what you would think. So we have a x value of 3 here. We're going to divide it by 3 to get 1. Now we have an x value of 1, 2, 3, 4, 5, 6 divided by 3, and then we get 2. And down here we're going to have the same situation. Divide negative 3 by 3 and we get negative 1. Divide negative 6 by 3 and we get negative 2. So we just connect those dots. And that is our dilated graph. So if we keep that green graph there, we can see that it was a horizontal compression. We took the green graph and we pushed it inwards from the right and the left. We pushed inwards from the right and inwards from the left, and it turned into the orange graph. Okay, so I want you to try a problem like that. Go and attempt number 34. When you come back, we'll do it together. Okay, we're back. Obviously, this is the linear parent relation, and y equals x is the parent equation. It's a vertical dilation because we're doing something to y, and of course we're multiplying, so it's a compression. Again, we're going to draw the same parent graph, which is going to look like this. And because we're multiplying y by 4, we're going to take all the y values on this graph and divide by 4, the exact opposite of what you would think. The y value of that point is 4, so we're going to divide by 4, we get 1. The y value of this point is negative 4, divide that by 4, and we get negative 1. And the y value here is negative 1, divide by 4, we get negative 1/4. The y value here is 1, so we get 1/4 when we divide by 4. And that's pretty much all we need to graph this relation. So that was a vertical compression. We're taking the orange graph and we're pushing up on it and pushing down on it to turn it into the green graph. If you got that one right, good job. Okay, so let's do this one together. This is obviously the absolute value parent relation, and y is equal to absolute value of x is the parent equation. And this is a horizontal dilation because we're doing something to x. But this is different. What's different about this? Well, we're dividing x. In all the previous problems, we were multiplying. Multiply y or x, but now we're dividing. So it's a horizontal stretch. Not a compression, it's a stretch. Whenever you divide x or y, it stretches the corresponding graph. So if we draw the parent graph, which we've done already twice, it looks like that. Now we're dividing x, so that means we're going to take all the x values on this graph and we're going to multiply them by 2. Not divide by 2, we're going to multiply them by 2. So this x value is 1. I'm going to multiply it by 2, and so I'm going to have an x value of 2. This x value is 2. I'm going to multiply that by 2, and I get 4. This x value is 3. Multiply that by 3, or excuse me, multiply the x value, which is 3, by 2, and you get 6. So 1, 2, 3, 4, 5, 6. We're multiplying all the x values by 2. And we're going to do the same thing on the other side. So we get these points. And we're just going to connect the dots. And of course the origin stays the same. If you multiply 0 by 2, it's not going to change 0. Whoops. I don't want to go outside our window. So as you can see, it's the same thing as compression. It's just instead of dividing all the x values, you multiply all the x values by 2, the exact opposite of what you would think. Remember, it's always the opposite of what you would think. We're dividing x by 2, so you would think that you would take all the x values and divide by 2, but no. You multiply all the x values by 2. So that was a horizontal stretch. We took the red graph and we stretched it out. We pushed it out to the right and out to the left, and it became the purple graph. So again, it's just the same situation. We're doing the same thing over and over and over again. Let's try another one of these. This is the square root parent relation, because we have a square root and y is equal to square root x. That's the equation. This is a vertical dilation. Why do I say that? Well, because we're doing something to y. Whenever you do anything to y, multiply or divide that is, it's a vertical dilation, and it's a stretch because we're dividing. It's a vertical stretch. If you look at the parent equation, it looks like this, or the parent graph that is, it looks like that. But we're going to multiply all the y values by 3. Why multiply? Because again, it's the exact opposite of what you would see in this equation. It looks like the y values are being divided by 3, but the y values are actually being multiplied by 3. It's the exact opposite of what you would think. So the y value here is 1, so we're going to multiply by 3, and we get that y value there. The y value here is 2. If you multiply 2 by 3, then you get 6. 1, 2, 3, 4, 5, 6. And 0 doesn't change, so we can just connect the dots at that point. I mean, the point 0, 0 doesn't change, so there you go. So maybe we should keep that previous graph, and you can see it's called a vertical stretch because we pulled up on the green graph to get the purple graph. We pulled up on it. Okay, on to 37. So the parent relation is obviously the cubic relation because we have something cubed, and y equals x cubed is the parent equation. This is a horizontal dilation because we're dividing x. Whenever you do anything to x, it's a horizontal dilation, and it's a stretch because we're dividing x. So if we look at the parent graph, it's going to look something like this. Again, this is on your library of relations. But we're going to take every x value and multiply by 2, the exact opposite of what you would think it would be. X is divided by 2 in this equation, but we're going to do the exact opposite. We're going to multiply all the x values by 2. So this x value is 1. Multiply by 2, we get this x value. This x value is -1. Multiply by 2, we get -2. And we have an x value that is 2 that's way up here. But that point is off the scale, so we're going to have to use the equation. So let's go to the equation. Remember, sometimes you have to go to the equation. So let's plug in, if you plug in 3, we're going to get a fraction. So let's plug in 4 for x. 4 divided by 2 is 2, and then 2 cubed is 8. So that's already off the scale. So we're just going to have to graph what we have so far. And there you go. So we took the purple graph and we stretched it out. We pulled it out and it became the pink graph. Alright, let's try one more of these before you do one on your own. This is the quadratic parent relation, because we have an x that's squared, and the parent equation is y is equal to x squared. This is a vertical dilation because we're multiplying, actually we're dividing y. Whenever you do anything to y, specifically multiply or divide y, it's a vertical dilation, and of course it's a stretch because we're dividing. Whenever you divide, it's a stretch. So the parent equation looks something like this. If you look at your library of relations, we're going to multiply all the y values by 3, because in the equation we're dividing y by 3. When you divide y by 3 in the equation, that means you multiply all the y values. So this y value is 1, so I'm going to multiply that by 3, so we get this y value. Same thing on the other side. And if we go any further, it looks like we're going to go off the scale, so we can just connect the dots and we're done. So we took the graph that looks something like this and we stretched it vertically. We kind of pulled up on the green graph, pulled up with those orange arrows. We pulled it up and the green became the purple. Again, this can be very confusing to interpret what's going on, but just remember the rules and you'll be okay. Try number 39. Remember, it's going to be a stretch because we're dividing y. And whenever you multiply or divide y, it's going to be a vertical dilation. Try 39. When you come back, we'll do it together. Okay, we're back. So this is the absolute value parent relation, and the parent equation is y is equal to absolute value of x, obviously. This is a vertical dilation, and it's a stretch, because whenever you're dividing y or x, it's always a stretch. The absolute value graph looks like this, but we're going to multiply all the y values, because when you're dividing y in the equation, you multiply all the y values in the graph. So the y value here is 1, so I'm going to multiply that by 4. So I get a y value up here. And the y value here is 2. Multiply that by 4, we get 8, so we're already off the scale. That's all the way up there. So I'm going to connect the dots, and that point up there is off our scale, but at least it gives us some reference as to where our line should be going. Then I can erase those dots up there. So this was a vertical stretch, which means that we took that orange graph and we stretched it up, and it became the red graph. So if you got that answer, good job. Okay, we'll just do 3 more of these and then we'll be done for the day. At least I'll be done. You'll need to do your homework though. The parent relation is the quadratic. The quadratic relation, the parent equation is y is equal to x squared. And this is a horizontal dilation because we're dividing x. Whenever you multiply or divide x, it's a horizontal dilation, and it's a stretch because we're dividing. Okay, so this equation looks like so. But we're dividing x, so that means we're going to, instead of dividing all the x values by 2, we're going to multiply all the x values by 2. So this x value is 2. Actually, that should be up here. This is 2. So we multiply that by 2, and we get an x value of 4. Same thing over here, except it's negative 4. This x value is negative 1. We're going to multiply it by 4, or actually 2 when we get negative 2. Same thing over here. And that's about it. So now we can connect the dots. And there you go. So we took that pink graph and we stretched it horizontally. We stretched it out and it became the purple graph. So we got that one right. Good job. Let's try 41. Go ahead and try 41. When you come back, we'll do it together. All right, we're back. The parent relation is obviously the square root parent relation. The parent equation is y is equal to square root x. And this is a horizontal dilation because we're dividing x. Whenever you divide or multiply x, it's a horizontal dilation, and it's a stretch because we're dividing. Whenever you divide x or divide y, it's a horizontal stretch. So if you graph the parent relation, use your reference points, it looks something like that. But we're going to multiply all the x values by 3. Again, it's the exact opposite of what you would think. You would say, well, we're dividing all the x values by 3. Not on the graph. In the equation, we're dividing x by 3, but on the graph, it's the exact opposite of what you would think. We're going to multiply all the x values by 3. So this x value is 1, multiply that by 3, and we get this x value. This x value is 4, multiply that by 3, and you go off the graph. It's somewhere out here. So we can connect the dots. 0, 0 doesn't change. And there you go. It's going to look something like that. You don't need to get any more accurate than that. So our graph did look like this, but we horizontally stretched it. So we took the orange and we stretched it out, and it became the green graph. So if you got that one right, good job. Try number 42. When you come back, we'll do it together. Okay, we're back. The parent relation is the cubic relation. The parent equation is y is equal to x cubed. And this is a vertical dilation because we're dividing y. Whenever you multiply or divide y, it's always a vertical dilation. And it's a stretch. Whenever you divide, it's always a stretch. If we plot the parent graph, it looks like so. But we're going to take all the y values of the points on that graph, and we're going to multiply by 2, the exact opposite of what you would think it would be. So I'm going to multiply this y value by 2. That y value is 1, so you multiply it by 2 and you get 2. This y value is negative 1, you multiply it by 2, you get negative 2. And I think that's going to be it. Anything else is going to be off the graph. So now we just connect the dots. We could find some more points to make our graph more accurate, but that's okay. So there you go. That was the class today. Let's go ahead and take screenshots to help you with your homework or to study for tests. So here's screenshot number 1, screenshot number 2, and screenshot number 3, and number 4, and number 5, and number 6, and number 7, and number 8, and number 9, and number 10. But don't go before you get your homework. Let's see what the homework is. Remember, if you don't do this homework, it's a 100% guarantee you're going to learn nothing in this entire course. So get a screenshot of that homework. and you must do the homework correctly. So be sure to get a picture of the answers. Make sure you did all these problems correctly. It's not enough just to attempt the homework. You must do it correctly. No excuses whatsoever. So there's the answers. So you should have 3 pictures total for the homework. Get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.